Artificial intelligence is now seen as the next major computing revolution, with computational capabilities far beyond traditional algorithms. This technology has applications across numerous sectors, including Formula One, where it is already being used in various areas. One of the most interesting is aerodynamic analysis, with the potential to reduce the reliance on wind tunnels and traditional tools in the future. CFD programs for virtual simulations start with equations describing physical phenomena to predict the behavior of an aerodynamic component, calculating how speed, pressure, and forces generated by the air interact with the surface. However, CFD models are always simplified compared to reality, as a complete physical analysis would be too time-consuming and resource-intensive. Since not every aspect can be considered, design teams must choose only the most relevant ones. This involves deciding which phenomena to analyze, such as whether to focus solely on aerodynamics or also on thermal aspects, whether to study stationary or transient behavior, and most importantly, at what scale of turbulence, with vortices ranging from microscopic sizes to several meters in diameter. Wind tunnels also have limitations, as they cannot accurately replicate how a car behaves in the real world. For instance, it is possible to analyze a car at various heights from the ground, but its movements on the suspension cannot be simulated, preventing data collection in more dynamic conditions. Additionally, the ability to study a physical phenomenon depends on the availability of sensors to measure key parameters, not to mention the difficulty in controlling air temperature, which modern cars are highly sensitive to. As a result, CFD and wind tunnels are useful tools for developing a rough idea of a particular solution, but only the track can provide the final verdict. Contrary to popular belief, artificial intelligence is not a recent development. Theoretical foundations were laid decades ago, but only in recent years have processors reached the necessary computing power to apply them. For example, in the 1990s, Benetton experimented with neural networks to improve the drivability and vehicle dynamics of their cars. While CFD starts from physical laws to study the behavior of an aerodynamic solution, artificial intelligence algorithms work in the opposite way. They start with existing examples, identifying trends in available data to predict the behavior of new solutions or the same object under different conditions. AI's reasoning is therefore deductive based on known information. A prerequisite is building a database, a large sample of data that, in the case of aerodynamics, can come from the track, wind tunnels, or computational fluid dynamics analysis, which is necessary to train the model to recognize trends and predict different scenarios. Formula One is no stranger to this technology, having already used it in developing the 2022 regulations. The focus then was on the aerodynamic disturbance caused by the car ahead, requiring a study of the turbulent wake, which was extremely complex to model and analyze in computational fluid dynamics. The FIA and Formula One, however, also exploited the predictive power of machine learning, with algorithms maturing to the point where they could predict the behavior of the turbulent wake at a distance of 1 meter and up to 40 meters behind the car. An earlier case was with Porsche, when between 2017 and 2018, they developed the EVO version of their 919 hybrid LMP1 prototype. In designing the rear wing, the German manufacturer started with an existing database of 1,600 wing profiles, training a computational model to identify key parameters like chord, geometry, and curvature. The goal was to map the genes that describe the DNA of each profile, identifying 5 key parameters. However, with 5 values per parameter, 2 overlapping flaps on the same wing, and other variables such as incidence and relative distance, the possible combinations exceeded 30 billion. At that point, Porsche used another machine learning algorithm to solve the optimization problem. The model returned hundreds to a few thousand of the most promising configurations, which were then virtually simulated using traditional CFD analysis with a cluster. The sample size was progressively reduced until reaching the final wing configuration, which was then verified in a wind tunnel. The Porsche example highlights how, in its various forms, artificial intelligence can cooperate with traditional simulation tools without necessarily replacing them. As seen, these models use deductive logic, but are still limited in replicating human intuition. To explore completely new shapes, concepts, or situations, AI requires an existing database, whereas for entirely novel explorations, computational fluid dynamics or wind tunnels must still be used, starting from the fundamental physics. Furthermore, traditional tools can be employed to verify AI's predictions, as was the case with the Porsche 919 hybrid EVO. This does not diminish the immense potential of artificial intelligence, going beyond the limits of computational fluid dynamics and wind tunnels. In recent years, there has been much talk about teams investing in infrastructure, modernizing production departments, and building new wind tunnels. However, research and development in artificial intelligence could make an even bigger difference in the medium-term future, much like CFD did at the end of the 1990s and early 2000s. Computer technology therefore continues to advance, with CFD simulations becoming more sophisticated and artificial intelligence now a reality in Formula One. Yet, traditional wind tunnels remain essential for now, with several teams building new ones. McLaren's wind tunnel in Woking went into service in October 2023, Aston Martin's is nearing completion, and Red Bull plans to build theirs by 2026. Ground effect currently causes significant correlation issues with the real world, but a state-of-the-art wind tunnel still offers several advantages. Having ample space is the main added value. Over the years, Formula One cars have become longer, wider, and taller, with some teams limited by wind tunnels originally designed for smaller cars. As the scaled model approaches the walls of the simulation chamber, the airflow around the car starts to interact with the walls and ceiling, skewing the results. This problem is exacerbated by the recurring outwash philosophy, with aerodynamics pushing wheel turbulence outward, increasing the risk of interaction with the sidewalls. McLaren is a prime example of this. The new wind tunnel, inaugurated last October, features a larger simulation chamber, allowing for more accurate vehicle testing with wider steering angles and yaw without the risk of interaction with the walls. These are conditions mainly experienced in medium to low-speed corners, where the Woking car has made the most significant progress compared to past seasons. Another key aspect is the sensor technology used for data collection. Some sensors can be replaced, upgraded, or added throughout the life of the wind tunnel, but there's more freedom when building a facility from scratch, equipping it with cutting-edge technology. Sensors range from load cells under the central platform, measuring the distribution of forces on the four wheels, to instruments monitoring airspeed, pressure, and turbulence. It's not just the sensitivity and accuracy of measurements that matter, but also the intrusiveness of the sensors, with the goal of minimizing interference with the airflow. A common technique, particle image velocimetry, where small solid particles are blown into the tunnel as tracers. These are illuminated by lasers, while a camera system takes rapid photos to visualize the flow structure. However, its application is often limited to certain parts of the car due to the high computational demands, a constraint that encourages constant technological upgrades. One of the most expensive elements of a wind tunnel is the moving belt under the scale model, responsible for wheel rotation. In the era of ground effect Formula One cars, teams aim to keep the car as close to the ground as possible to maximize the load from the floor, operating at the edge of aerodynamic instability phenomena like porpoising. However, due to the high costs, teams are cautious about letting the model scrape against the belt, fearing damage and thus unable to simulate conditions where the car hits the ground.